Hi everyone, welcome to Organ Technology Part 8, Schober Organ Part 3, keying circuits. Well, why am I calling this also, subtitling it Schober Organ Part 3? Well, two of the first videos I ever posted on my YouTube channel here, and kind of what got me started doing a YouTube channel, was that I acquired a Schober organ, and I intended to do some videos of it as I restored that Schober organ. And a lot of people have found those videos and have asked me, hey, whatever happened to this project? So because it relates so perfectly to this part of our exploration of organ technology, well, it makes sense to also point this out as Schober Organ Part 3. Plus, there's a possibility that I am going to continue to do something with the Schober organ. So first, let's go a little brief look at what the Schober organ is about. When I was a kid, I wanted a practice organ. I wanted something serious, you know, two full-size keyboards, a full-size pedal board, so that I could, you know, because I was an aspiring professional organist. And stuff from Rogers was just a little too expensive for what my family could afford. I discovered that there was this company called Schober that built these kits, and they were much more affordable. But I never really got one of those. I ended up with a used organ instead, and that's just fine. But I've always kind of had this sentimental attachment to the Schober Organ Company. And so when a friend of mine who she and her husband back in the 70s had built a Schober organ wanted to give it to me, I thought, oh, yeah, here we go. I finally get my Schober organ. Brought it home, started really digging into it, started making some videos because I really fully intended to restore this thing and make it all like new again. But I discovered that, of course, well, all the power supplies were shot. Well, that was to be expected, but power supplies can be rebuilt or replaced. And but the kicker, the real kicker on this thing was the fact that the keying circuits were shot. Now, the Schober organ utilized a mechanical keying system very similar to what Hammond organ, tone wheel organs used. So in a Hammond organ, the tone wheel generator is constantly running and it's sending out its pitches. And then you have the appropriate pitch for pitches, all 9 of them, for every key has all these, what is called a key comb, and so you'll have your sub-octave, unison, octave, and super octave, and then you have running the other direction the buses, so when you hit a key, boom, they all come together, and when you hit a bunch of keys, all of the sub-octave pitches are going on the sub-octave bus, and all the unison pitches are going on the unison bus, and then that goes into the drawbars, and that goes out to the amplifiers. Similarly, Schober had the same thing. Their tone generator was constantly running, and you did the same kind of key comb trick to route those pitches out to a series of voice cards instead of the drawbars. Well, the thing was that on the Schober, the keyboard and the key comb system were really an integral part of each other. And it wasn't going to really work out to try and restore all of that. It was just too far gone, too wore out. I could maybe get the key comb thing to work, but then it was designed around a specific keyboard, and that keyboard was going to really be challenged to fix. But, you know, so I decided to use the Schober console for what is being called the Franken organ. That's a story for a whole other video. And but I kept all of the Schober components because in the back of my mind it was like, you know, I'd really like to do something with that stuff just because it's a piece of my childhood that would be fun to hear. So at any rate, today we're going to talk about keying circuits. Now, Hammond and Schober and a lot of other organ companies used a mechanical system for routing the oscillator pitches out to some kind of voice filter to achieve all of the different stops on the organ. Well, the better and more sophisticated way to do it would be to use a gate system. an electronic solid-state gate system. That way you have a single contact on the keyboard. It goes out to some circuitry. It's that circuitry that routes those pitches out to the buses and then to the filter cards, and then we hear the sounds of the various stops. So today we're going to be taking a look at some of that stuff. So the first thing we're taking a look at here are a couple of single oscillator divider network tone generators. Now, the Schober generator, here is our oscillator. Here is our special divider circuit. This gives us the top 12 pitches. The oscillators on this type of system generally run at 2 megahertz, way above human hearing. And then this special chip divides and redivides and does all this convoluted stuff to create the top octave. And so then we can take that top note and divide it in half and get the next one down, and divide it in half and get the next one down, and so forth. So then we push out our top C and we divide it in half and get the next C down, divide it in half, get the next C down, do the same thing with the B, the A sharp, the G, A, the G sharp, and so forth. And then over here on these pins, we have all of those pitches. So C, 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 B, 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 and so forth. Now, what are all of these resistors about? Well, on the Schober system, the Schober voice cards, and we looked at these in an earlier video, they want to see a sawtooth wave. But the oscillator outputs a square wave. So the resistors are to create a stair-stepped sawtooth wave. So what you have is all of these pitches are fed through a series of resistors and produce a new pitch. And then that way you can have a sawtooth wave going out at all of the C pitches. So the pitches that are divided off of this are used over and over and over again. And again, we talked about that in an earlier video. Now, there was another company that built nice kits for putting an organ together, and that's what this stuff is about. Now, here is a much simpler tone generator that uses the exact same principle and the exact same chips. We have our oscillator, we have our special divider circuit to generate the top octave, and then we have all of our subsequent divider circuits to generate all the C's, all the C sharps, all the D's, and so forth. This outputs a square wave, and in the Devtronics system, their filter cards wanted to see a square wave coming in. So just a slightly different circuit. The only difference in the filter circuits, if you are using square waves and you want to convert that into a sine wave, you have to use one circuit. If you're using a sawtooth wave and you want to convert that into a sine wave, you have to use a slightly different circuit. So it's just a different approach to the exact same problem. But where Devtronics really had something on Schober was in this monstrosity right here. This is a diode keyer. And so what happens is all of our pitches come in on the bottom here. We've got starting at low, well, low C is over here, and then we go all the way up to high C. All of those pitches are routed out to these daughter boards. That's these uprights sitting in here. If I turn this over, you can kind of see. Here's how all of this is routed. Here's the routing traces, and then here's our daughter board traces. We have pedal. We can have a third manual or a second touch, and then we have our accompaniment and our solo. And so what happens is on these ribbon cables, this is where our keying, slide that over, this is where our keyboard information comes in, and then that goes out to the appropriate note. So we got C, C sharp D, D sharp E, and so forth. And then the first 32 have diode keyers for the pedal to route the sub-octave, unison octave, and super octave. And then we have our keyboards. We also have some pitches routed over here for sound effects devices off of the pedal. And then all of that goes out to the filter system. So, how does it actually work? Well, let's take a look at some drawings. Here we have our keying voltage comes in here. It lights up this bus, and then that goes out to our 4 diode gate circuits. The voltage comes in to a voltage divider circuit, 2 equal value resistors, then through this diode, and then it goes over here to another diode, path to ground, and this is where our tone generator comes in. So here's the pitch for our super octave, and it is supposed to make its way over here to the output, which would continue on to the filter circuits. And you know, honestly, this is where I have a hard time visualizing these diode gate circuits. You know, it's hard to see exactly what's happening here. And the description that's given in the instructions for this circuit for somebody to build this thing, what it says is that the tone generator voltage cannot pass through these diodes and continue on to the output bus. Until the keying circuit is complete, the diodes become forward biased and therefore become conductive and allows the voltage to come out. Well, that's not exactly clear, is it? At least not to me. Maybe you see that. For me, understanding a gate circuit is much easier when we look at a transistor gate. Now, the Devtronics system used an additional gate system to send all of these pitches from their keying circuit out to a separate filter circuit specifically for a unit tibia. And here we have a series of transistors. So our stop switch comes down. This is just an amplifier signal to boost the signal going to all of the keying transistors. That's so we don't overload the stop switch. Here we have the output of our diode gate goes through the transistor and then onto a separate filter circuit. To me, a transistor is a lot easier to understand because you have a voltage here at the base, and that makes the transistor conductive. So our stop switch goes down, the bases of these all line up, so now the gates are open and the tone can go from here to here. On this diode gate circuit, that's not really as clear, but there's a little bit of a hint in all of this. What is a transistor? Well, a transistor is literally 2 diodes fused together. And so is that what's creating our conductive path? Is this effectively the base and then this goes through? Well, not exactly. So let's look at a similar circuit used in a Rogers organ. So I drew this out to make it a little easier to see, but you know, I don't know. We'll see here. Now, and the Rogers is using a similar system. So we have our pitches coming in from our oscillators here. Our key comes down and we have a very similar diode gate circuit, and then we head on out to the filters. So, and again, wow, I'm having a hard time visualizing exactly what's going on here. Well, the description in the Rogers technical manual was much more clear. What's actually happening here is that when we have a voltage here and we have our oscillator here, what's going on is the oscillator is serving as a control to the keying voltage. What actually goes out to the filter is the keying voltage as controlled by the oscillator voltage. So when the oscillator goes high, the keying voltage goes high. When the oscillator goes low, the keying voltage goes low. So the keying voltage is being made to follow the oscillator. So we have our keying voltage here. When the oscillator goes up, the keying voltage goes up. When the oscillator goes down, the keying voltage goes down. So it doesn't really matter, does it, that we're not actually hearing the oscillator tone, because it's not, at this point, really a tone at all. It only becomes a tone after it goes through a speaker. If you remember part 1 of this series, we talked about how there's actually no such thing as sound. So what happens here is the oscillator is controlling the keying voltage. The controlled keying voltage is now mimicking the oscillator's path and goes on out to the filter, then to the amp. The voltage then is oscillating a speaker cone, and it's the oscillating speaker cone that causes a compression wave in the air, and then we hear what we interpret as sound. Now, when you're using individual oscillators, as the Rogers organ does, you also have the option of dedicating a set of oscillators to a specific task. When you're using one of these diode gate systems, the whole point of this is to have a bank of oscillators that are going to do several things. So in a typical Rogers theater organ, like these drawings came from the 33E technical manual, we have a bank of oscillators that are strictly for the tibia, and then we have a second bank of oscillators that are for basically everything else. So on the main oscillators, just like in the Devtronics setup where we have a single oscillator divider network putting out all the tones, on the Rogers system we have individual oscillators putting out all the tones. But in both cases, the tone generator is always on. It's pumping its oscillation in at all times, and it's the keying voltage and the gate circuit that allow that to go through for a particular pitch to a specific filter circuit. But in the Rogers system, we have a second set of oscillators that are not on all the time because they only do one task. They only produce the tibia. So here we have our stop switch and our key, which combine to send a voltage out to the oscillator. When that control voltage goes out to the oscillator starts oscillating. That goes to a filter circuit, then onto the amplifier, and then the speaker cone mimics and we hear the sound. In the Devtronics system, they use the single tone generator and key it in two different ways. They key it to a series of filter cards, and then they also key it to a secondary filter to produce the tibia. So it kind of is the same result, just done with a similar system. So how does this fit with the Schober system? Well, remember at the beginning I said that the problem with the Schober organ was the mechanical keying system that was really impractical to restore. The Schober tone generator and the Devtronics tone generator both use the same chipsets and both operate at the same 15 volts. Could I use this Devtronics keyer to gate the tones, the sawtooth tones, off of the Schober tone generator and thus restore the Schober system and be able to use it again? Well, the only way to really answer that question is going to be through some careful experimentation. Now, in theory, the Schober tone generator and the Devtronics tone generator are using the exact not only the same principle, but basically the same circuitry. It's the same chipsets, the same square wave oscillator. It's just that the Schober tone generator takes the extra step of creating these stair-stepped sawtooth waves for its filter card system. In theory, I should be able to connect the Schober tone generator to the Devtronics diode gate keyer and ultimately get exactly the same result as the mechanical keying system. So I could prove all of this if I had an oscilloscope, but I don't, and so I'm just going to have to hook up do some careful experiments and just see, will the diode gate from Devtronics actually pass the Schober sawtooth waves and then be connected to the Schober filter cards. Well, we'll see, and if that happens, then that opens the door for actually restoring the Schober organ in some form. You know, it'll be a fun experiment either way, and so we'll just have to wait and see what happens with that next. So I hope this was informative. I've included a couple of other videos here. Now, for me, visualizing how a diode gate works in terms of electron flow has always been a little problematic. Understanding how a transistor works, where you open the transistor by putting a voltage at the base and then it allows a current, that just is more logical in my mind for some reason. But the fact of the matter is, what I'm visualizing is not actually what's happening. So I've included links to both the earlier Schober organ videos, so you can see what I talked about in those. But also a couple of interesting videos. One is on the true nature of electricity. You see, we think of electricity as electrons flowing through a wire, but that's not exactly what's happening. And maybe that's why I have a hard time picturing how a diode gate works. I've also included 2 videos from a really wonderful channel called The Engineering Mindset that explains really well exactly how a diode and a transistor actually works. So be sure to check those out. Hope you've had a good time today. I certainly had a good time talking to you about organ technology, and we'll see you in part 9, hopefully not too far into the future. Thank you much. See you next time.